auto transformer. So far we considered a two winding transformer as a means for changing the level of a given voltage to a desired voltage level. For example, if you want to step up the voltage from 200 to 400 volts or 400 to 200 volts, if you are stepping down, we used to do the two winding transformer. Two winding transformer. In the two winding transformer, there is a transfer of electrical energy or electrical power from one circuit to the other circuit is purely on electromagnetic induction that we have studied. That is, it may be recalled that two winding transformer has two separate magnetic coupled coils. These are wound on a common magnetic core with no electrical connection between them. There is as such there is no electrical connection between the primary to the secondary winding. The transfer of the electrical energy is purely on electromagnetic induction. In this session, we shall show that change of voltage level, that is either stepping up of the voltage or stepping down of the voltage, can be achieved by quite effectively using only one winding transformer, that is using the auto transformer. It is possible to change one voltage to another voltage level by using a single coil only. Such transformer having single coil with suitable tappings. There are different tappings. Suppose I want to change the voltage level from the 400 is the input voltage. I want to get around to 20 volts. Then there is certain setting for 20 volts, 40 volts, 60 volts, 80 volts, 100 volts, so on. Means then the input voltage what you are getting giving is the constant, and across the secondary you got a different tapping, so that at a different voltage level you can tap the voltage from the secondary winding. Auto transformer or commercially they are known as variac because we are getting a variable voltage supply across the secondary, or it is also called as the dimmer and it is an important piece of equipment in the any laboratories. Means the variable voltage you are getting from this variac, or it is also called as the dimmer. Now we will how exactly it is working, how there is a variable voltage we are getting across secondary, that we will study with the help of a diagram. Suppose I have got a winding between B and C. I have got around 200 turns here. Then I am applying a voltage of around 400 volts 50 hertz to this winding, BC winding. It is consist of two turns. Then the voltage across each turn, or the voltage per turn, is equal to 400 divided by 200, means each turn, across each turn we have got a voltage of 2 volts. Therefore, there is a total 400 volts and there are 200 turns. Then the voltage per turn is the 2 volts. That is between, there is a one winding between B and C. Okay. If you take out a wire from one end of the coil, say C, that is I am taking one winding from the point C, the another point from any tapping point from the E. If you take out a wire from one end of the coil, say C, and take out another tapped from any arbitrary point E, any suitable, any voltage level if you want, you can tap it from the another point from the E. Now we would expect some voltage available between the point E and C. Definitely there is a voltage is between E and C, because between E and C there are certain number of turns they are available between E and C. Therefore, the voltage available between E and C is equal to NEC into 2 volts, because each turn having a voltage of 2 volts. Therefore, there are NEC turns in between E and C. Therefore, what he is telling is the magnitude of the voltage will be obviously 2 into NEC. 2 means it is a 2 volts per turn. 2 into NEC is number of turns between E and C. If tapping is made at point E is such that the number of turns between E and C is 100. I am taking an example of 100 turns between E and C. then the voltage available between E and C is 100 into 2, that is the 200 volts what I am getting. That is from the 400 volts, I am getting the 200 volts here with a single winding. It is a single winding. Therefore, this is called as the auto transformer. If you want to change the tapping from 100 turns to 150 turns, in that case, the voltage available between E and C is 150 into 2, that is 300 volts. Like that, there is a variable voltage you are getting across E and C depending upon the tapping on the auto transformer. Thus, we have been able to change 400 volts input voltage to a 200 volt output voltage by using a single coil only. Therefore, this is how the single phase transformer, auto transformer works. Then we will compare the two winding transformer with the auto transformer. Then while comparing the two transformer, that is one is two winding transformer, another one is auto transformer. In that case, we are considering here the two winding transformer is also transferring the same amount of the energy from the primary to secondary, and in the auto transformer also same amount of the energy is transferred from primary to secondary with the same voltage level of the primary and the secondary voltage. For example, if you want a transfer 2 kVA of electrical energy using the two winding transformer, then you have to compare the 2 kVA transformer with it has to auto transformer with the 2 kVA, then the voltage level is 400 to 200, 400 to 200, whatever may be the case. Means the same amount of energy should be transferred, the same amount of voltage level should be changed in the two transformer. Then you can compare the two transformer for their design, the saving of the copper, what are the advantage and the disadvantage of the auto transformer, that you can study. Now we will consider here, we find that to change the given voltage V1 to another level of V2 and to transfer the given kVA from one side to another side. Means for both the transformer we are taking the same kVA, same V1, same V2 for two winding transformer in one hand, then in another hand we have got auto transformer with the same kVA, with the same V1 and V2. We have choice, namely by using two winding transformer or by using the auto transformer. You can transfer the given amount of energy either by two winding transformer or auto transformer. There are some advantages and disadvantages associated with either of them. Then to understand this aspect, let us compare the two types of transformer in equal terms. Means the input voltage V1, output voltage V2 for both two winding transformer and auto transformer is same. The rated current of supplied by the primary or load current is I2, corresponding the supply current is I1 for both the two winding transformer in one hand and the auto transformer in the other hand. Then if the kVA to be handled by both the types of the transformer, in that case, that is V1 I1 must be equal to V2 I2. That is quite evident in the conventional type of transformer. That is kVA rating is depending upon, it is a product of V1 I1 that must be equal to product of V2 I2. Means for both transformer we want V1 from the primary, V2 from the secondary. Load current it should be supplied by two winding transformer is also I2, auto transformer is also I2, and there the kVA rating remains same, that is V1 I1 must be equal to V2 I2. This can be explained with the help of this particular diagram. Can look into, I have got a two winding transformer. Here I have got V1 I1 and I have got V2 I2 in the secondary. That is the input and output. At the same time, I have got the auto transformer here. Here also V1 I1 of this is same as V1 I1 of this. V2 I2 of the auto transformer is same as V2 I2 of the auto transformer. Means I am comparing one by one, that is auto transformer with two winding transformer. Let us now write down the MMF balance equation of the transformer. MMF is nothing but it is a product of the number of turns into a current. Okay, If you consider a two winding transformer, what is the primary MMF? The primary MMF is, it is a product of number of turns into current, that is, it is N1 and I1. And MMF for secondary is, it is once again the number of turns multiplied by the current, here it is N2 I2. Here for the two winding transformer, MMF balance equation is N1 I1 must be equal to N2 I2. Similarly, if you are considering for the auto transformer, if you are considering for the auto transformer, in this case the MMF balance equation is, that is, the MMF for the B to E. If you are considering B to E, the number of turns is, the total number of turns is, here it is N1, here it is N2. Between B and C it is N1, between E and C it is N2. Therefore, the number of turns between B and E is N1 minus N2. It is N1 minus N2. And what is the MMF here? The MMF here is, it is N1 minus N2 into I1. The current which is flowing here is I1. Then similarly, what is the MMF in the between E and C? The MMF between E and C is, the number of turns between E and C is N2, and the current which is flowing in this winding is I1 minus I2. I1 minus I2. Therefore, it is N1 minus N2 I1 must be equal to N2 into bracket I2 minus I1. If we are simplifying this, once again what we are getting is, that is N1 I1 must be equal to N2 I2. Means the MMF of the primary must be equal to MMF of the secondary. Okay, it is for both the two winding transformer as well as the auto transformer. Find out the ratio of the amount of copper required in two types of transformer. How there is a saving of the copper in the auto transformer, that we have to demonstrate here. Therefore, the copper required, that is nothing, noting that the volume of the copper required will be proportional to product of current and the number of turns of a particular coil. That is, the copper required for a transformer is proportional to the number of turns multiplied by the current. That is, the volume of copper required is proportional to number of turns multiplied by the current. Why it so? That is, total amount of volume of the copper required is depending upon the cross-sectional area as well as the current carrying capacity. That is the length. Okay, that is, the volume of the copper required is proportional to cross-sectional area into length. Cross-sectional area into length. The cross-sectional area of the conductor required is proportional to current. Therefore, it is I. And the length of the wire is depending upon the number of turns. Therefore, it is proportional to N2. Therefore, the copper required is proportional to, it is N into I. Therefore, the same thing I am writing here. This is because length of the copper wire is proportional to the number of turns, and the cross-sectional area of the wire is proportional to the current value. That is, volume of the copper is proportional to the length of the wire multiplied by the cross-sectional area of the conductor. That is, the value of the copper is proportional to length of wire multiplied by cross-sectional area of the conductor. Therefore, the volume of the copper is proportional to N into I. Volume of the copper required is proportional to N into I. Therefore, now I am comparing with the two different transformers. First, I am taking amount of copper required in the auto transformer. That is, what is the amount of copper required is proportional to N into I. What are the N into I? That we will see for the auto transformer. That is, the copper required for this particular portion is proportional to, it is N1 minus N2 into I1 plus N2 into I1 minus I2. is the total copper required. Is it not? The copper required for this initial portion between B and E is the number of turns is N1 minus N2 and the current which is flowing is I1. That is N1 minus N2 into I1 plus N2 into I1 minus I2. Same thing is written here. That is N1 minus N2 into I1 plus N2 into I2 minus I1. Then if you are simplifying this particular the equation, what I am getting is 2 times N1 I1 minus N2 I1. Here the one small the corrections are the what you have to substitute. How we are getting this N1 I1 2 times N1 I1 is equal to 2 times N2 I1, that because we are already derived N1 I1 is equal to N2 I2. What I am getting here is it is N1 I1 minus N2 I1, here N2 I2 minus it is N2 I1. Then if you are simplifying, and after simplifying, then what I am getting here is it is one term, what I am getting is N2 I2 here, the N2 I2. N2 I2 can be replaced by N1 I1, therefore there is a N1 I1 here and it is N2 I2 here, then what I am getting is total N1, 2 N1 I1 and 2 N2 I1. And similarly here N2 I2 is replaced by N1 I1, so that what I am getting is 2 N1 I1. Therefore, what I am getting the ratio between the copper required with the auto transformer to the two winding transformer is 1 by K. Okay. Then weight of copper required in the auto transformer, that I am representing by WA is equal to what is the, that is 1 minus K times the amount of copper required in the auto transformer. Just you have to make use of this formula, that is the ratio. Then what I am getting is amount of copper required in the auto transformer is 1 minus K times amount of copper required in the two winding transformer. Therefore, it is what I am getting is 1 minus K times weight in the ordinary transformer, that I am representing by W0. Therefore, in terms of WA is equal to 1 minus K times W0. It is auto transformer, copper required for ordinary transformer. Then saving means it is a WA minus W0, or here W0 is more, therefore W0 minus WA is the saving. W0 minus WA, what I am getting here is it is WA, and instead of W0, I am putting this value, that is saving of the copper is equal to W0 minus WA. Actually it is W0, it is not a WA, it is a W0, that you have to make the correction here. That is, here I am making this is W0, W0 minus 1 minus K times W0, so that what I am getting here is K times W0. Saving of the copper is K times W0. If you are using the auto transformer, you are saving K times W0 of the copper. Therefore, saving in the copper, if you are using the auto transformer for transferring the same capacity of the energy with the same voltage level change, then what we are getting here is K times weight of the copper required in the ordinary transformer. This is the advantage of the auto transformer.